The Grocery Manufacturers of America reported that 76% of consumers read the ingredients listed on a product's label. Assume the population proportion is P equal 0.76 and a sample of 400 consumers is selected from the population. In the picture here I have set up the sampling distribution. I want to check to see if that's normal. Now this is not the central limit theorem, so that I can say samples of size 30 or greater, the sampling distribution can be considered normal. These are population percentage and sample percentages, and I'm relying upon a different criteria to determine whether I can say that the sampling distribution is normal. This is important if I'm going to use the normal probability density function the way I have in the past to approximate these probabilities. I want to make sure that the distribution I have is normal. So there's two conditions here that if they're met, we can go ahead and assume that. The sample size is 400 and the population percentage is estimated at 0.76. So that calculates out to 304, and that's certainly greater than or equal to 5. So we're okay on that one. And then 400 times 1 minus 0.76, or 0.24, calculates out to be 96. And again, we're greater than or equal to 5. So I can definitely assume that the distribution I've drawn here is normal. Now, I've set up the interval. It says that what is the probability that the sample proportion will be within 3 percentage points, or 0.03, of the population proportion. So that's anywhere from 0.73 to 0.79. I'm also going to need the standard deviation of this distribution, and we're sampling here, so it's the standard error. This is a different formula than it is for averages. This formula would have me take the p-value, the population value here, multiply it by 1 minus p, and divide by the sample size. Now, notice that I'm taking the square root of that whole thing, and that calculates out to 0.0214. So I've determined that the sampling distribution is normal. The center of the sampling distribution is the population percentage at 0.76. And the standard error, or standard deviation of the sampling distribution, is 0.0214. Now, to find the probability that a sample proportion taken from a sample of size 400 would fall within 3 percentage points of the 0.76, or somewhere between 0.73 and 0.79, I have to find the area under the density function above the interval. Since the sampling distribution is being modeled by the normal probability density function, I can proceed pretty much the way I have in the past. I need to calculate the probability that 0.73 is less than or equal to p bar, the sample proportion, less than or equal to 0.79. And I need to calculate a z-score for the 0.79. So I'm going to subtract the 0.76, divide by the standard deviation, the sampling distribution, also called standard error, and I get 1.40. So the 0.79 has a z-score of 1.40. And the 0.73, since it's the same distance and I have symmetry, is a negative 1.40. I'm going to go to the standard normal table and look up the 0.140, and I get 0.9192. Then I'm going to go look up the negative 1.40. Get 0.0808. So with those two values, I can go and find the probability that my sample proportion taken from a sample of size 400, the probability that it would be between 0.73 and 0.79. Calculate that by finding the probability that my z-value is between negative 1.4 and 1.4. And to get that middle area there, the middle part that I want, I'm going to have to subtract the 0.9192, subtract 0.0808, and end up with 0.8384, or 83.8%. So, if I go out and take a random sample of 400 consumers and ask them whether they read the ingredients on product labels, calculate the percentage that do, then there's an 83.8% probability that that percentage that I calculate will be somewhere between 73% and 79%. Saying it another way, if I take a random sample of 400 and another random sample of 400, another random sample of 400, then 83.8% of the sample percentages that I would calculate on those samples, 83.8% would fall somewhere between 73% and 79%.